Hello everybody, I'm Dan. Welcome to my Java tutorial series. Throughout my tutorials I will teach you Java using just Notepad and the command prompt. The order in which my tutorials are organized on both my website at javacjava.com and my YouTube playlist is designed to maximize learning by building on concepts from prior tutorials. This tutorial is about the isProbablePrime method from the BigInteger class, and this is part 1 of that tutorial. Okay, first things first, let's go ahead and open up a web browser to my website, javacjava.com, select Java Tutorials. And we'll scroll all the way down here to the BigInteger isProbablePrime tutorial. Now in this tutorial I'm going to discuss the isProbablePrime method. It returns false if the BigInteger object value is definitely composite. It returns true if the BigInteger object is probably prime. So let's take a look at this up here. Here's the declaration for this here. We've got isProbablePrime method, and then we have one single parameter of primitive int type, and that is certainty, and I'll explain what that is here. So I just talked about the return values. So if the numbers being tested is returns false if the numbers being tested is definitely composite, excuse me, or it returns true if the object value is probably prime. And I'll explain what all that means here in a second. So the method is extremely fast for determining if a number is composite. You know, maybe they should have named this method isComposite instead, right? So why did they name it isProbablePrime anyway? Well, we've got to talk about what's called the Miller-Rabin primality test. Now, the reason this method is so fast is because it uses the Miller-Rabin primality test. The math and proofs behind the Miller-Rabin primality test is way beyond the scope of this tutorial, but I will do my best to describe the general idea of how it works. So a multiple, which is the int certainty parameter up here, right, of tests, or in other words algorithms, are performed on random numbers that are less than the number we are trying to determine the primality of. Now the more tests that you perform, the higher probability that a true result will actually be a prime number. Setting the certainty parameter to 80 or more will almost always indicate that a number is prime if the result is true. Now, because of the way the algorithm works, if the result is false, then the number is composite. It is important to note that when an MR test, the Miller-Rabin test, returns false, we will have no idea what any of the factors are. So let's go ahead and get started here. Let's come down here and highlight the source code. You know what I want to do? I'll do that later there. Let's highlight the source code. Jeez, they're going crazy here. Alright, Control C to copy, or right click and select copy. Let's go ahead and move the browser off screen here. I've got a shortcut to the command prompt on my desktop, but if you don't, you can create one really fast by right clicking, selecting new shortcut, CMD next and finish. It's just that easy. Let's go ahead and open up the command prompt. First thing you want to do is type in javac, which is Java compiler command. You should see all this stuff scroll by. However, if you receive an error message, watch one of my tutorials on installing and configuring the Java runtime for your particular version of operating system there. Okay, let's go and type in CLS to clear the screen, CD space / CD short for change directories, / tells it to go to the root. Well, I'll make a directory here called Java with the MD command, and I already have that folder, but if you don't, I'm going to create one for you. Let's change directories to the Java folder. Let's make a directory here called Prime1. Okay, let's change directories to the Prime1 folder, and let's notepad up prime1.java will be the name of our source code file, also known as a compilation unit. Let's go ahead and paste the source code in here. And I am going to comment out this last section right here. We'll come back to that here in just a second there. Alright, so what we're going to do here is I've got, actually what I need to do, I'm not sure I grabbed all that rest of that source code. I think I did, yeah. I need one more import statement here, java.util. Let's grab everything from the util package. Alright. So prime1, name of our class. I have got basically this constant up here, even though there's no such thing as a constant, but it's a int, primitive int type, and setting equal to 10. And then in the main method entry point here, I'm declaring a BigInteger reference variable 2 equal to a new BigInteger object that holds the value of 2. and a new BigInteger reference variable bi that holds the value, or refers to the value of a big integer that contains the value of 1. Now, 2 is the first prime number, so we're just going to display that to the screen here. What I'm going to do is we're going to display prime numbers to the screen, and we're going to record the amount of time it takes to calculate these prime numbers here. Okay, so I'm just going to start off with an int variable I and setting that equal to 1, and then I've got this while statement right down here while I is less than nth prime, right? And we're starting nth prime out equal to 10. And I am just storing the current time in milliseconds, the system current time in milliseconds, to the start time here, so we can see how long this while loop takes to actually complete. So this while loop will just basically add 2 to the big integer object, which originally contains 1. So our first value is going to be 3. And we're going to be checking to see if that is a probable prime number, and we're going to be passing 80 in for the certainty. And we're going to change this number throughout the tutorial here. And then we'll add I to that, and then we'll just display BI to the console if, in fact, it is a probable prime. Okay. Now, once it's all done, it will display the nth prime number is, and it'll display that. And it'll display the time to calc. So let's go ahead and run this here real quick. And let's do Java 6. Let's go ahead and clear our screen. Java C to compile this. Java to run it. Okay. So these are our first 10 prime numbers, 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. So the 10th prime number is 29, and the time to calculate that was 10 milliseconds. All right, let's go ahead and display the first 100 prime numbers to the console here. And let's save this, come back up here, clear our screen, recompile, and rerun. Okay, so the 100th prime number is 541. All right, I'm going to bring back over my web browser, and I have in my other tab up here called the nth prime page, and it's at primes.utm.edu/nth prime. And so we can type into this little field here just to confirm our results. So if we want to display the 100th prime, right? The 100th prime is 541, okay? We're going to put in the 1000th prime right here, which is 7919. Okay, so let's come back over here, let's modify our program here, and let's do the 1000th prime. And this will display the first 1000 primes to the console, and the 1000th prime number is 7919, which is exactly what we were expecting. All right, let's bump this up here to the 10,000. Let's display the first 10,000 prime numbers to the console here. And there we go. And while that's going, we'll bring this over here and we'll do the 10,000th prime, which should be 104,729, and it is 104,729. Okay, so that took 6,141 milliseconds, in other words, 6.1 seconds approximately. Now what's taking all the time here is actually displaying this big integer object, converting it to a string and displaying it to the console. So let's go ahead and comment out this line and see how much time we save. Again, we were at 6.1 seconds there. Let's recompile this and rerun it. Okay, now we are less than a second, 814 milliseconds. And you can see here our 10,000th prime is that number right there, which is in fact that. Okay, we're going to go up to the 100,000th prime and see what that is. So that should be equal to 1.2 million approximately there. Let's just change this to the 100,000th. File, save, and come back up, recompile, rerun. Okay, now we're not displaying this, obviously. You can see it's running its calculations here. And we should end up with, oh, wait, where did that go? Yep, oh, come back here. 1299709, 1299709. That took 7.4 seconds approximately there. So let's talk about this number certainty here. And now we've got an 80, which is basically means that it's going to perform a whole bunch of tests to make sure that it's prime. What if we just lop this number in half and change that to 40? Will our 100,000th prime still be equal to that? In other words, you know, will all of the 100,000 primes that it would be displaying to the screen, are we going to get it all there? See, 12999,709. So we're still getting the same result here. Let's chop this down, but as you can see, that only took 4.2 seconds as opposed to 7.4 seconds. Let's change this value to 10, okay? All right, and we get that in 1.9 seconds. Still, it's 1299709, so we've got it all done right there. Let's change this value. Let's lop it down again to 5 and see what happens there. We saved a little bit of time, not much, but we still got the same number. Let's change this to 3, and let's save that. Okay, now you can see we're off. 1299709 is what we should have gotten. 1299647. So it found and threw in a couple of extra composite numbers into our while loop there, and we ended up with the wrong 100,000th prime number. So you can see we do end up saving time. So there's a trade-off all the way in between, say, for example, when we were running it way back up here at 80. Let's put this right back to 80. And I think it was... Yeah, we'll just run it again here. So... As we could see, when this number right here, that was set at 5 for the certainty, and now we set it back up to 80, and let's see how long that takes. So 5, we got it down to 1.7 seconds, and this is probably going to be much, much longer here. And basically what I'm trying to do is reiterate here that basically, you know, the higher you make that number right, the bigger probability that you're going to be returning back prime numbers, but then of course the longer it takes to perform this operation here. And what we'll do is while that's running there, we'll just come out here and we'll change this to 1 million, right? And let's change our certainty back down to 5, and let's see if we still get accurate results all the way up to there. So, actually, you know what I'm going to do? I'm going to change that maybe to like 6. Just a little extra certainty there. Well, anyway, you can see how long this is taking, and I'm just going to go ahead and kill that program there, right? And let's clear our screen. Let's recompile, and let's run that. Okay, so it's calculating out the first million primes, and let's see what the millionth prime number actually is. So the millionth prime number is 15,485,863. So let's see what we get there. How long that takes to get all those. We got this set to 6, 1 million, and good to go right there. Okay, so there we are. 15,485,863. That took 18.4 seconds to calculate the first million prime numbers. If we actually uncomment this line out here, right, we'll get to see them scroll by as we do. But, however, you know, that'll just take a lot longer because of it's converting all these big integer objects there. Okay, so I'll do Control-C, we'll just kill that. All right, so what I'm going to do now is I am going to go ahead and comment all of this out here. Talk about just a couple other things here before we move on to the next tutorial here. All right. Let's save that. So as you can see, it's pretty fast as far as calculating primes, creating like prime. You can store all this stuff into an array if you wanted to have the first million primes in an array in very, very fast, short order there. So now let's talk about something else here. I'm just going to go ahead and run this and then go over the code here. So let's come up here, let's recompile, rerun. We're done with that, and what I've got here is I've got big integer variable random1 referring to a new big integer object that is 1,000. If you remember this constructor from my big integer constructors tutorial, this creates a 1023-bit prime probably prime number, of random value. Okay, this 80 is the certainty, which is the same thing up in isProbablePrime. Then random, and so basically that number right here is this one right here. Random 1 is this big giant number here. So this number here is most likely prime. It's a very, very high probability this is prime. And now I've also created another one here called random 2, which is another big integer object of 1026 bits, 80 on the certainty, and of course just randomly created it here. All right. So here is our next number right here. What I'm going to do, I'm actually going to clear the screen. I wanted to get a different result here. 2049. That's close enough, whatever. This number down here. Okay, so displaying these to the console right here, and then I am creating this other big integer object that product points to here by multiplying random 1 by random 2, right? And we get this big, this is the product of those two being multiplied together is this giant number right here. Now we know this is a composite number here, but what I've displayed to the console next is its bit length, and you can see it's 2049. I wanted to actually get this 2048, but because of the randomness of these numbers, it's hard to actually get a 2048. And then I'm invoking the isProbablePrime method on there, passing it, with certainty of 10, right? And isProbablePrime, remember back, that'll return false if in fact this number is guaranteed to be composite. And there it is, it's composite. As a matter of fact, we know that. It's made up of this number and this number. I'm going to clear the screen one more time, hoping I will get, there we go. Okay. So 2048-bit, right? You've probably heard of this in 2048-bit encryption, RSA encryption. And basically in a nutshell, the way this works is this would be like a public key. And this number is made up of two very large prime numbers, okay? Now, if you're just looking at this number right here and you don't know either one of these is what's called the keys, right? So you don't know what either one of these keys are, then it's almost impossible computing time to take and basically if you figure out the square root of this number and then basically every number in between, prime number in between 3 and all the way up to the square root of this number, approximate square root of this number plus 1, you would have to factor it out and divide it by only prime numbers, right, in order to eventually hit this number or this number, right? Well, actually, you wouldn't hit this number because it's larger than the square root. But this first number here is smaller than the square root because it's 1023-bit. This next one's 1026-bit. So anyway, I just kind of wanted to show you that. This is going to kind of lead into next tutorial that I do on that stuff there. I'm going to go ahead and get rid of this and get rid of that and just leave you guys with some final thoughts on this here. So. Stay tuned for my next tutorial where I will discuss some more concepts about RSA encryption and how the isProbablePrime method can be used to try to determine the prime factors of large public keys. That concludes this tutorial. Thanks for watching.